thermodynamics. Last but not least is Tran from Clemson University, who's going to talk about chemistry of quantum materials. Thanks for coming.
Hello everyone, thank you very much for sticking around. Thank you, Martin, for the kind invitations. I hope you can hear me okay. All right. Or I can just yell and not use the microphone. So yeah, it's been really great to visit Georgia Tech. It's actually my first time here at Georgia Tech. So yeah, it's awesome, very different from Clemson. So all right, so from Stone Age, Bronze Age, Iron Age, and very much right now we say we live in Silicon Age. But the Silicon Revolution very soon coming to an end because we are approaching the physical limitations set by the size of the silicon atom in your electronic devices. So the question now becomes, what's next? What is the material that will shape our future? And I actually don't have answers to those questions. I don't know. But I think we kind of have a guess here. So the rapid advancement of quantum technology, and the goal is to be able to creatively utilize quantum effect in order to create, process, transmit coherent information. And quantum materials provide a good platform for that because we can chemically modify a material. You can also assemble the material in extended framework, and then you can also integrate material into the current or the catalyst technology. However, the catch is that up to this point, there's still very poor understanding of what is the underlying. We have very poor control over atomic precisions and structural tunability, and also electronic tunability that required for all the functionality that enable the quantum coherent information. So the way that we our lab, the way we approach the research is that we start with a dream. For example, what I just shared with you a second ago, and going along with the dream, there's a challenge always associated with that. And we would like to think in terms of what a chemical principle that allows us to address that current fundamental technological challenge. And then we come up with the idea of, for example, what elements do we want to utilize? What symmetry do we should be looking at, and what type of lattice contribution that would be a best place to start? And then we could go to the lab and create material, and then we characterize structural and physical properties of material by using single crystal powder action diffractions, physical property measurement, and also we also use neutron diffraction and X-ray synchrotron diffraction. National laboratories as well. And for completion, we also do density functional theory computation in order to understand what type of chemical bonding and what type of overlapping that give rise to the functionality or physical behavior of materials. So for us, a good day is that the material we created exhibit the functionality that we were hoping for. But I told my students that maybe a better day is that when what we create didn't really give us what we are looking for, and then we can have a chat about what can we tune, what can we play around with in terms of can we move the Fermi level up a little bit, or can we increase the number of spin number, or can we increase spin orbital coupling a little bit further. So having that kind of chat within the group, I think that will be a better day. So I think it's just all about, I think sports, that's psychology. So I think we should have science psychology as well, right? So either we have a good day or a better day. So that's not a bad day. Okay. So here is a research program that I'm doing in Clemson. We actually are a relatively young group. We've been around maybe 3.5 years or so. So we have a lot to learn from all the wonderful people here. but I can give you a snapshot of what we are interested in at the moment. So, specifically, we try to find a way to chemical logic in order to realize the logical spin texture. And also the other system is how can you then integrate spin into spin phonon interface. So one of the things I have realized in the material community, so I feel like that either people focus a lot on mechanism or focus on optical. So I'm a little bit fortunate because I have a mixed background between the two. So I wonder if I can bring these two elements to unite them in one system for them by using, in this case, for example, mixed ligand in lambda. And also in the hope that what we're doing here, we hope to build a map, actually, build a map to help us navigate, where should we go if we're looking for specific functionality of materials. So for today, I will be focusing on this box, some limited new adventures in quantum spin liquid. And I will start with a review paper that we put together a couple of years ago. And then I will finish up with the most current work in collaboration with Martin on a layer 3-dimensional spin 3.5 magnet. Okay, so as I mentioned earlier, for the quantum information science. So in classical computing, we use classical bit, which is 0 and or 1, right? But in quantum computing, you have used qubit, which is 0 and 1 at the same time. So for this, we utilize quantum superpositions, like showing the cat up here, like the cat alive and dead at the same time until you open the box. And the other phenomenon is quantum entanglement, right? The entangled particle. And I would have been overlooked if I didn't mention the Nobel Prize in Physics 2022 for the experiment of entangled photon for 3 scientists here on the pictures. So we need these 2 components, superposition and entanglement. So that takes us to the hope that a state of matter called quantum spin liquid can help address the challenges that we are experiencing in quantum information science. Because the catch, so at the moment, there are 2 main technology that I'm aware of. Either they use superconductor or they use trap ion or silicon and also a defect, diamond defect. So for superconductors, a lot of superconductor, for example, IBM, they actually use tungsten telluride, and they build quantum computer based on that. And they admit that the good thing is that they have very good speed, like it's fast, right? Gate is fast, and gate is just a fancy way of saying that the microwave pulse. But however, if the fidelity, they sacrifice fidelity, so fidelity is not good enough. But for silicon a defect or diamond defect or trap ion, for example, trap ion they have very high fidelity. But on the other hand, gate is not fast enough. But in either case, we both suffer by for the qubit, they're very susceptible to the external qualification, like the environment, like defect and room temperature operation. So can we realize a state of matter that inherently allow us to have superposition and entanglement, right? And so that's why we look into this quantum spin liquid, and for spin 1.5 on 1-dimensional chain is a classical example. So in math, you have an infinite 1-dimensional chain of spin 1.5. So for the scenario A, you have spin up, down, etc. Or B, you have down, up. So A and B, right? You would say they have exactly the same energy, and they have also the same probability to exist. So you can say that they degenerate, or the ground state what you have in the superposition, like A and B is. So why it's hard? Because so let's say, right, if we were to line up like this and engage and pay attention, and so it will look like this, right? But most of the time, what we will see in reality is that either we have this order, or the spin pair up, right, in a long range order fashion. So that's why it's actually tricky. In real material, for example, the idea is that how can we find a sweet spot where we have good enough disorder, and also we have sizable complete exchange interaction, but not right. We don't want not too strong, not good, too weak, not good either. So where would be the best place to look? So for example, here you see the particle law system, either you have a spin glass or the disorder, or which undergoes a long range order fashion. So how to search for spin quantum liquids? So you can more welcome to check out this paper if you like. But to sum up, you want to look for a system that features geometrically frustrated, like what Mike was discussing. For example, if you have a triangular lattice, right? So it's impossible to simultaneously satisfy AFM, antiferromagnetic exchange interactions for each pair. So for example, we have spin up and again spin down here. So the first one can be either up or down, and in this case, result you have a degeneracy. You have the graph say really the mixture of many other spin configurations. Okay, so that's where to start. For two-dimensional, you can look into triangular Calamari honeycomb lattice, and for three-dimensional diamond and particle law. So in this review paper, the author mentions, we mentioned that you want to look for spin half system or pseudo spin. And it back 2 years ago, but then now Morton actually I just brought up another video you can see here. So here I'm quoting here in the paper. So anisotropic large spin systems are not reordered, right? And novel quantum excitation with their classical counterpart can be realized in a fully ordered magnet. So actually this gives us more hope that we can actually expand our horizon a little bit and look into the place that we haven't yet looked into in order to study and learn more, and we will be able to utilize the quantum effect in quantum technology. But in any case, I would like to leave you a few questions to think about. So does quantum spin limit grounds actually exist in real material? And do they have any relevance to the real world? Well, my answer to that first two questions is also very quantum mechanic. Probably yes, I don't know. But and then the third one is that to what extent, as I mentioned, you balance. We need to look for a sweet spot, right? And to what extent a disorder can influence the behavior. And then finally, this question actually can sometimes keep me awake at night. Like, can we find a better way, have better control over the atomic scale precision with structural and electronic tunability, so that we can chemically tune the computer exchange interaction that required for realizing quantum effect? Because at the moment, right, it's still it would be nice if we have a solid, like a GPS that help us navigate, where should we go. So that takes me to the second part of my talk. So is there any way that we can chemically tune the computing exchange interactions? And the way we approach our work is just based on a very simple connections here, right? It's crystal structure, electronic structure, and physical behavior. So the idea is that if we can modify the central Hamiltonian, in addition to Heisenberg exchange interaction, in this case for a triangular lattice. And if we also induce an anisotropic asymmetric exchange interaction, and we can make it a little more sizable, right? So that it can also compete with the Heisenberg exchange interactions. And what would we get? Because in order to induce the DM exchange direction, we will need a system that lacks of inversion center symmetry and significant large spin orbital coupling. So we need broken inversion center symmetry, right? And also coupled with the triangular frustrated lattice. So, and also inspired by Martin's, we look into anisotropic large spin, and then we add a noncentrosymmetric structure. So let's say we have a layer of triangular layer stacking along C, but if you look at this one, there's actually no inversion center symmetry, right? That this structure can accommodate. So then what will we get out of that? So that is in my student Zudong. He created this material, the CaMn₂O₆. It is a spin 3/2 triangular magnet, and here is the crystals. So you see it's a two-dimensional spin 3/2, the pink, the Mn here, right? And also tellurium actually on the same layer with manganese. And the calcium in between the layer. Okay. So now if you look at the habit of the crystal, you see that we actually onto something that we have some trouble here. So this material crystallized in noncentrosymmetric spiral triangle trigonal structure spectrum B312. So you can look at the symmetry and you say, okay, there's no cinematic absence here. So how can you tell that you are actually looking at the correct space? So we verified with not only single crystal diffraction, powder, 11 BM synchrotron X-ray, and later we also verified with PDF and Neutron. So this is the spray group that allows us to describe the structure with the least disorder and the highest symmetry. But as you see, it's sort of like a stacking fall here along, say, it's a layer, it's hexagonal plate crystals, but you see there's some stacking fall here, just looking at the physical. So, and actually this is true. So you look at it again, it's a horrible fit, right? You look at the first pick here because of the before orientations. But the reason we think it's useful because you can look and see that it's whether we're missing the C-axis, right? Whether the C-axis here 3 times longer than what we presented. So that the answer to that is no, because if it was 3 times longer than that, we would have seen the first peak in a low cube here. I'm sorry, not here, a low angle, right? So. And because of that reason, so we were not satisfied with the structure derived from single crystal powder, single crystal and powdered fractions, and also 11 BM. So we look into PDF analysis, and a friend of mine, Utah, she helped us with the PDF analysis, and here is the result from the PDF, and here's a fitting from PDF. And the result here consistent with what we see, which is we have a stacking sequence where the Mn and the tellurium switch every 3 layers. So as you see, Mn, and then tellurium here, and then continue. So it's switch every position every 3 layers or so. And then okay, but why does it matter? Because if we didn't look deeply enough, we would have reported as a honeycomb lattice. Because if you have Mn and tellurium in the same plane and they look like so then we would have this is honeycomb lattice. And then we will go down to the entire graph. We will be a disaster. So the point that what we've learned from here is that it actually works, taking a step back and making sure that things come together, making sure we're not this is triangular magnet is not a honeycomb lattice. Okay, so let's look at the magnet susceptibility here. It's Mn 4+, you can see from the chemical formula, and the spin 3/2. So the magnet susceptibility, and here the revised analysis that resulted in the effective moment 3.9 μV, which is consistent with the spin 3/2 system. However, you see it actually undergoes a magnetic phase transition, but it's very subtle. So you wouldn't see it from the chi-d by itself. So when you take the derivative here, you see there's a value at around 10 Kelvin. And when you look at magnetic susceptibility at a function of temperature under a series of magnetic fields, so you see that there are a few kind of changing in the slope in low field, and then suggesting maybe there's some AFM and FM competing exchange interaction. However, that actually been suppressed by in higher field. Now, so you take the dA over dt as a function of temperature. What we're seeing is that the transition temperature it can increase as the magnetic field increase, which is meaning that we're onto something here a little bit, right? Because typically we would expect the other way around. So then meaning that maybe we would have some field-induced magnetic phase transitions. So what is the thermodynamic of the ground state of the material? So we look into specific heat data, which is the change in energy with respect to change in temperature at a constant pressure. So there are two main contributions to heat capacity. You have magnetism or conduction electron and phonon, which is lattice vibrations. So and we also would want to look into the phonon contribution in terms of acoustic phonon and an optic phonon, and we use the bind Einstein model in order to analyze the phonon contribution data. So acoustic phonon, okay, sorry, I'm running out of time. So here the heat capacity data. So me now, a friend of mine in Poland, help us measure the data. Heat capacity. So what you see here, the anomaly heat capacity at around 10 Kelvin, consistent with what we see in magnetization. And the phonon contribution here can be described by 2D bind mode. And if you see the color green here. And the delta S max can be extracted by taking this integral. And we're approaching about 100%. So we recover 100% entropy across the phase transition for screen 3 indicating that it undergoes a long range magnetic ordering. So we would like to look a little bit deeper into low temperature regime, and Martin Tali help us with the measurements. So here the low temperature heat capacity measurements. So I want to show you on the left, in the Schottky anomaly, and you see actually the Schottky effect suppresses by magnetic field. See it's at 14 Tesla, 9 and 0. And we do the fitting here, so we can extract the Schottky gap, extract it from the fitting, and proportional to this value, to this contribution from the magnetic field, from the magnetic moment, and also the applied. And we look at it a little bit deeper by using the model built by Alan, also a friend of mine. We overlap at Johns Hopkins. So here the capacity function of temperatures. We model this below 1K at the nuclear Schottky anomaly, and then fit it power law for electronic heat capacity. And here the result, you see it fits nicely with 1.352 MeV, which is agree very well with the refined static model from the Neutron data that I'm going to show you right now. Right, but in the magnetic ground state. So here's Alan. So here the Neutron diffraction data using XP to a beamline, and you see the material undergoes a long range magnetic order around 8 Kelvin. And here the magnetic structure can be described by the propagation vector a third at 0.353. So from here you can see that the incommensurate magnetic ground state. And here the refined moment 1.39, which is consistent with the low temperature heat capacity that I show you earlier. So now to the physics static moment, right, which is only about 45% of the full S3 half value of 3 MeV. So maybe it suggests there's some potential, some low line magnetic excitation, and or maybe some entanglement between spin. And here the magnetic ground state in the AP plane. This is 120 new manifold, but it is spin actually rotated about 127 degrees from the spin below. And this is actually quite significant because if you will think about it, like if it was an FM exchange between the layer, then there will be the angle will be 0. But if it's an AFM between the layer by itself, it will be, and the angle will be 360, right? But then here the angle here you see 127, which is actually very sizable. And the incommensurate spiral along the z-axis direction. So this is suggests that the competing exchange direction are very significant. So what is the overlapping that gives rise to that phenomenon? So if you look here, the band structure and density of state. So you look at the band structure, it's rather diffuse. That indicates that it's more directional, right? Meaning that you have some anisotropic here and rather the overlapping of the waveform is rather directional. It's not flat. And the MND states polarized, right? Which is the direct evidence for magnetism. And then the D state, MN internal polarized oxygen P state. And you see a very good overlapping between MND and oxygen P. And we take it all together, you can see that you can chemically, we can chemically tune the way that the spin communicate in this triangular lattice. And we look careful in order to realize it's actually got a triangle, not the honeycomb lattice. And when you can induce some noncentrosymmetric, if the broken inversion center symmetry in the structure, you can then realize the incommensurate magnetic ground state. And so it just suggests that something that hopefully you can use, you can consider when you think about one way in order to chemically modify the competing exchange, and a way in order to potentially facilitate the entanglement between spin in a new class of quantum material. So with that, I would like to thank my collaborators, my group here at Clemson, and Oak Ridge National Lab, Argonne, and NSF for the support. And thank you very much for coming to my talk. Sorry, I'm over time 5 minutes back.
Thanks a lot, Thao, for quoting our words of defeat, the quantum spin liquid search. Are there any questions for Thao?
So you said that we shouldn't just look for spin half systems for trying to find quantum spinning. So sort of you chose spin 3 halves. Is there any correct connection between whether you choose integer and half integer spins, and also does the coordination of the lattice tell you something about whether or not we're more likely to see these long-range entangled spins?
Yeah, okay, that's excellent, thank you. So you're right. So if what you want to look at quantum spin liquid, right? The good place to start is with spin 1/2, right? But then to point to that. Because for the small spin number, right, spin quantized. So when you look at the small spin number, the better chain that you can realize the quantum mechanic behavior rather than classical, right? And however, right, the small spin number is not only way. I just pointed out here by Martin in order to, if you want to realize, like the novel quantum excitation, but for half integer spin, you have a chain in order to have pseudo spin mark, right? For half integer, right? But integer spin form too, like spin 1 is also a lot of fun to work with. So in this case, I think half integer spin, as I mentioned, you get a chain to get pseudo spin 1/2. If you have spin over coupling, for example, and then it gap out, and then you have J effectively, right? But I think large spin number shouldn't be discount in the search for quantum effects. Okay, and then you have another thing in terms of the lattice of the spin, right?
Oh yeah, so Does the coordination also determine anything about whether you're more likely to see interesting? Obviously, if you've got frustration, that's great.
Yeah, that's actually a good point. For example, here using within the AB plane, right? Most the Heisenberg AFM within the AB plane. But what happening in the plane, like between the planes, in this case, I would propose what we need further evidence at the moment. I'm not confident to say that between the plane we have sizable asymmetric exchange DMs. Because by DM is impossible, but in addition, there's also the stacking pole here. And I'm not sure if it might be doing something funny to the system as well. So I'm being careful about saying what's going on between the plane. But whatever that is, it actually significant. If you look at the rotation angle between the spin from the plane above and below, it's 127 degrees. It's size enough. Good point. Thank you. Yeah.
So what would happen if you had
Yeah, that's possible. That one thing, I think that what I want to answering on his question. Yeah, I think it's possible that we have, and that the screen channel you suggesting is that has something to do with the stacking pole.
yeah,
Yeah. Right.
kind of
Yeah. I think it's possible. And but yeah, we again we need more measurement. I think Martin would ask me, can we grow a 5 gram crystal of this material? Like, try. Yes.
worried about
No, that would be
what the final sign is.
yeah, that would be awesome. Yeah, yeah, that would be fantastic. Thank you.
Thao, can you grow 1 gram crystal material?
Like,
More seriously, so is this a family of material you can explore? So can you change the metal and keep the similar structure, or
yeah,
is this a playground, or is it a unique material?
actually, yeah.
A weird material?
That is theory. Actually, there are quite a few of them. You know, it's a system. It's not just a one-off kind of thing. You know, what naturally question we would ask ourselves is that can we create a vanadium 4+ version of this? So back to your point, vanadium 4+ is being one half. But yeah, you can play around with this. So for on the previously reported similar system, when we look, you see that most of them reported is a honeycomb pattern. And I think the second point here is tricky. And yeah, so there are a lot need to be done in order to confirm this. Maybe animal would help it further here. But I think in a moment, yeah, this is as good as we can get with this model.
Any other questions? Right. 2 more.
Yeah. Yeah. So my student have done the way he grew this materials is by mixing starting material including calcium carbonate, Mn, I believe chloride, and then tellurium oxide. And tellurium oxide acts as both starting material and also flux. So he brought it up to the temperature about 750 degrees C, followed by slow cool to 400 degrees C, and then quenched it. So that's how we got this hexagonal. Thank you.
Earlier in your talk, you mentioned how people either focus on the magnetism side of things or the optical side of things, and how you're trying to bridge the gap. Could you talk a little bit more towards that point and exactly how you're looking towards doing that?
Yeah, absolutely. Yeah, thank you. Great point. So here, right? Yeah, I didn't present this work at all. But but there's a way to do it. So for example, when you can couple frustrated magnet in a triangular or one-dimensional chain, for example. And then the optical response in this case, because if you excite material with the radiations, and you have the nonlinear optical response here, right, through the second harmonic generation, which is the capability of generating the coherent photon, right? So and the requirement for that is you need a structure that lack of inversion center symmetry. So because when it lacks inversion symmetry, your second order susceptibility is different from zero. So that gives you the signal, right? So that is so in this case, the idea is that if you create a noncentrosymmetric magnetic frustrated material, you can then couple magnetic and optical response. But that's not the only way. The other way you can do is actually there's a lot of fun things you can tinker with here. If let's say because you play around with lambda, if it's centrosymmetric, you don't need to look for nonlinear optical, you can look for luminescence. Right? So that's a way that if you want to couple magnetism and light, there's a way to do it. Right? Either magnetism and luminescence, you play around with lambda, or magnetism and nonlinear optical response, you can play around with anything you want, as long as you have magnetic component and as long as the structure is lack of inversion tendency.
So the first thing you're mentioning is essentially the quantum transduction idea, right? Where you excite the system at microwave frequencies and you get a response at optical frequencies.
Yeah.
But what you're proposing here is really the non-centrosymmetric photon of inversion. Any other questions for Thao? Well, if not, I'd like us to thank everybody today for coming and all the speakers who came from close and far. Thank you so much again, everybody. So tomorrow the workshop resumes at 9. Is that right, in this room? And you will have opportunity to interact with Rigaku folks to learn about capabilities and software. And for the invited speakers who are coming for dinner, I think it's at 6:30 p.m. tonight. And thanks again, everybody, for coming.